When it comes to the analysis of electric fields and the principles behind them and the concepts that kind of govern them, it's unbelievable how closely related gravitation, universal gravitation, is to the concept of electricity and electric fields. And for that very reason, in this video and in several future videos, I'm going to show you guys the connection between universal gravitation, which is something that we've spoken about in depth, and how all of that almost directly applies to electricity and electric fields, just with slight different variations in the terms and the variables that we use. So in this video, we're just going to talk about uniform fields. If you remember back, a uniform field would be like a classroom on the surface of the Earth. We know that the surface of the Earth would be down here, and the higher up in the classroom we are, the higher our altitude is. However, from the floor in the classroom to the ceiling is not a big enough change in altitude for there to really be a difference in the field up here than the field down here. Now, yes, these field lines are closer together. You do have a stronger force of gravity down here as opposed to you do up near the ceiling. However, it's such a small, negligible difference where you assume that the classroom has a uniform gravitational field. We know from the very beginning of the year that if we'd like to calculate the force of gravity in this uniform field, well, gravitational fields act on masses, so I would place some mass inside. And in order to calculate that force of gravity, it would quite simply equal that mass, the magnitude of that mass that I placed in that field, times little g. Now, at the beginning of the school year, we kind of were told that g is 9.81. Several people called it gravity. We kind of let that go in the beginning of the year. We now know more officially this is known as the gravitational field strength. So if you think about it, the force of gravity is just how much mass I have, and what is the strength of the gravitational field at that location. If we're talking about electric fields, a uniform electric field precisely, it's exactly the same concept with a few different variables. So here I have a positive plate and a negative plate. Think of this as like a rectangular piece of metal that I've stripped the electrons away from, and I've taken all those electrons and placed them on this rectangular metallic plate down here. So that creates this electric field between the two of them because any positive test charge that was placed in this field will be accelerated or pushed downward towards the negative plate. So just like I took a gravitational field and I inserted a mass, we're going to do the same thing, but electric fields don't act on masses. Electric fields act on charges. We use the letter Q, lowercase q, to represent charge. So just like m represents mass, and that's measured in kilograms, Q represents charge, and it's measured in what are known as coulombs, and it's represented with a capital C. So just like a mass is measured in kilograms, Q, or charge, is measured in coulombs. Similarly, I have a gravitational field strength up here. Same concept. This field has some kind of strength. We call it capital E for electric field strength. And much like gravitational field strength is newtons per kilogram, it's the amount of force per unit of mass. It's the same idea, but it's the amount of force in newtons per unit of charge. So instead of having kilograms and newtons per kilograms, we have charge, which is measured in coulombs, and electric field strength, which is measured in newtons per coulomb. So it's the same basic idea, the same basic principle. However, in this case, we're dealing with charge instead of mass, and therefore coulombs instead of kilograms. So just like in the gravitational field, if I wanted that gravitational force, I'll take the mass and multiply it by the field strength, the gravitational field strength. I will do the same thing down here. But we're not talking about masses anymore. We're talking about charges. So I replace the m with a q. And we're not talking about gravitational field strength. We're talking about electric field strength. So hopefully you can see it's the same basic idea. We're just using different variables. So to see an example really quickly, in the classroom, if you were told that this classroom is on the surface of Earth, and therefore the gravitational field strength is 9.81 newtons per kilogram, and you place a 3 kilogram mass in that field, well, the force of gravity will be mass times the field strength. 3 times 9.81 will give me 29.43 newtons. Similarly, and again, these field strength will not always be the same, but I made them all the same just to show you that the concepts are the same. If instead I had an electric field strength that was 9.81 newtons per coulomb, and I placed 3 coulombs of charge into that electric field, well, I would calculate it much the same way. The magnitude of the charge times the magnitude of the field strength. In this case, 3 times 9.81. and I'll also get 29.43 newtons. You will certainly get different values for different field strengths and different amounts of charge, but I did want to show you that the concept is identical. Instead of masses and gravitational field strengths, we're dealing with charges and electric field strengths, but those concepts are exactly the same. So the big takeaway from this example is that in order to calculate the force that acts on a particle, when I say particle, I mean a mass for a gravitational field, a charge for an electric field, a magnet for a magnetic field, and so on. If I want to calculate the force acting on that particle in a uniform field, one where the changes are small enough that they can be ignored, I simply multiply the magnitude of the particle by the strength of the field. So for gravity, which we've known since the beginning of the year, it's the magnitude of the mass times the gravitational field strength. And for the electric force, similarly, it's the magnitude of the charge times the magnitude of the electric field strength. So hopefully you see some of the connections here. Now really quickly to go back, if I look in that classroom again, there's a second thing that I can calculate. By throwing a mass into this gravitational field, not only can I calculate the force of gravity, but I can also calculate the potential energy, in this case the gravitational potential energy. And that equation, of course, we know is mgh, mass times the gravitational field strength times the height above some reference point, usually the floor. Well, similarly, trying to go along with this connection of the same concepts, just different variables, I can also calculate how much electric potential energy, as opposed to gravitational. Instead of mass, we use charge. Instead of gravitational field strength, we use electric field strength. And instead of the height above a reference point, we usually say the distance above a reference point. You could technically consider this h as well, but it gets a little bit trickier because if this field was sideways so that all the lines pointed to the left, well then you wouldn't really have a height. It's more like the distance from the right or left side. So that's the only reason why we use distance instead of height, because these fields do not always point down, whereas gravitational fields typically always point down. So again, just to show you an example and hopefully make this more concrete, in the classroom, if I have a field strength of 9.81 newtons per kilogram, I have a mass of 3 kilograms, and I hold it 2 meters above the ground. Hopefully you all realize the gravitational potential energy would be mgh, 3 times 9.81 times 2, and I would get 58.86 joules of gravitational potential energy. Similarly, if I set up a positive and negative plate so that I had an electric field in between, and the electric field strength was 9.81 newtons per coulomb, not per kilogram, per coulomb, and I placed 3 coulombs of charge 2 meters from that bottom plate, well, again, you realize I use charge instead of mass, I use electric field strength instead of gravitational field strength, and I use the distance above my reference point, in this case the negative plate, as opposed to the height above the ground, which in this case is also 2 meters. So when I multiply the same values, I'll get the same total amount of energy. Again, you will certainly get varying amounts of energy when we start using realistic numbers, but I'm trying to get across to you guys, and hopefully you see, the concepts are identical. It's just we don't use mass, we use charge. The field strength is electric instead of gravitational. So basically, to calculate the potential energy of a particle in a uniform field, multiply the magnitude of the particle, mass for gravitational fields, charge for electric fields, by the field strength, gravitational field strength, and electric field strength, as well as the height above some reference point. The height above the ground usually for a gravitational field, and the distance above some reference point, usually the negative plate, in an electric field. So hopefully you're starting to see the connection that the concepts are the same, the variables are the only things that are different. Now the only other thing that's a little bit different that we have to kind of take into account is it's fairly easy to tell whether a mass is gaining or losing potential energy, simply as am I raising it up or am I lowering it towards the ground. But with electric potential energy, it's a little bit trickier, and what I'm going to help you kind of come to terms with is figuring out whether the charge is gaining or losing the energy that we just calculated. And that comes down to one very important question. What does the particle want to do? I write want in quotes because obviously it doesn't want to do anything. But you need to think to yourself, what does the particle want to do? In this case, if this is a gravitational field, these masses want to be on the ground. If I let go of them, they're going to fall towards the ground. If you think about this for a second, objects doing what they want to do will lose energy. If I take a mass and I hold it up about 1 meter off the ground and let go of it, it will fall to the ground. And as it falls, it will be losing that energy. Yes, it will be converted to kinetic or sound or heat when it hits the ground, but it will be losing that potential energy. Just like if I did the opposite and raised the mass up, that mass is being forced to do the opposite of what it wants to do, and objects doing the opposite of what they want to do will gain energy. So if I take a look at this example, I have four masses, 1, 2, 3, and 4. In this case, if I'm raising this mass towards the ceiling, well, mass number 1 is gaining energy because it does not want to be up here. You're forcing it to do the opposite of what it wants to do. Yes, you're also increasing its height, which also increases its gravitational potential energy. Mass 2 is being moved directly to the right. It's not gaining height, it's not losing height, it's actually not being forced to do anything it wants to or does not want to do. And for that reason, there is no change in energy from mass 2. Mass 3 is being lowered towards the ground. That's what the mass would like to do, therefore it's losing energy. Yes, its height's decreasing as well, which is why, but it's doing what it wants to naturally do, so it loses energy. And hopefully by now you realize mass number 4 is being moved to the left. That's not what it wants to or does not want to do. Therefore, from mass number 4, there's no change in energy. This same concept can be applied to electric fields, as long as you remember to ask yourself, what does the particle want to do? So if I look at an electric field, we know that positive charges want to be near the negative plate naturally, and negative charges want to be near the positive plate. So if I take a look at case 1, I have a positive charge. It's being moved to the right. That is not being moved towards the positive, which is what it doesn't want to do. It's not being moved towards the negative, which it does want to do. It's actually neither, so that tells you there's no change in energy. Charge number 2 is negative and is being forced to be moved towards the negative plate. We know that that is not what it wants to do. Negatives do not want to be near other negatives. Therefore, that charge is gaining energy. Charge 3 is positive. It's being forced near the positive plate. Therefore, it is also gaining energy. Things that are forced to do what they don't want to do will gain energy. And last, charge number 4 is negative. It's being moved towards the positive plate. A negative would like to be near the positive. Therefore, that charge is losing energy. So the big takeaway, the big two takeaways, I guess, are that the force as well as the energy, in terms of electric force and electric potential energy, same concepts as gravitational fields. However, we substitute mass for charge, gravitational field for electric field, and the height above a reference point for the distance from a reference point. And if we want to know whether a charge is gaining or losing energy, we simply have to remember to ask ourselves, what is that charge? Is that charge doing what it wants to do or what it doesn't want to do? Charges doing what they like to do will be losing energy, and charges doing the opposite of what they like to do will be gaining energy.